Good morning to all. I am M. Visalakshi, Assistant Professor, Department of Electrical and Electronics Engineering in Tandai Periyar Government Institute of Technology, Vellore. Welcome to e-learning class. And today's topic about uh, basics of stability analysis from power system analysis. So today we are going to discuss about stability, basics of stability analysis, different types of stability and dynamics of synchronous rotor, swing equation with its derivation. So basically stability means stable. So stable operation of a synchronous machine which is connected to the power system when subjected to the sudden disturbance, or it's an ability of a power system to return the stable operation. Okay, also the term instability refers to loss of synchronism, means falling out of step of the synchronous machine in power system. So basically it has different types based on the nature of disturbance: transient stability, dynamic stability and steady state stability. So these are the three different types and we are going to see elaborately in next slide. So first one is transient stability. So it is mainly to determine whether the system is in synchronism or there is some sudden disturbance in transmission line, heavy loads, switching with heavy loads. So mainly the characteristics leads to loss of synchronism. When also the main aim of transient stability is to determine the system in synchronism. Okay, so next is dynamic stability. Dynamic stability of a system is mainly the amplitude of oscillation will be small and they die out quickly. Mainly for unstable system, the amplitude will be very large and exist long time. So these type of unstable may create some problems in power system operation, means unnecessary frequent load. Okay, so some changes means in turbine speed, change in load. Coming to steady state stability, it is mainly determining the upper limit of loading synchronism machines before losing synchronism. It is mainly assumed that the machine is loaded gradually. In power system, the small disturbance will continuously occur due to variation in load, changes in speed, fault in some part of the power systems. So this may exit the system in state of natural oscillation. Coming to large disturbance, it may occur in power system due to switching load, transmission line, some major faults. Okay, this sudden large disturbance can be assumed or evaluated by large changes in speed of the rotor of synchronism, changes in power angle and changes in power transfer. So here the main concept of stability is a single synchronous machine connected to infinite bus. Infinite bus means substation bus voltage and frequency is assumed to remain constant. Also, it is characterized which do not change the power supplied or consumed by any devices which is connected to it. So here the it is mainly equivalent to two different machines and having the system which running in synchronism. So next is a dynamics of synchronous machine or rotor. So here a synchronous machine, it's a rotating body which is applicable to it. So we are going to consider the kinetic energy. So here the mechanical losses in the system and electrical losses in stator are neglected. Okay, so here we know the general formula of kinetic energy, half mv square generally. So here the kinetic energy of the rotor of a synchronous machine is defined by E suffix ke will be equal to half j omega sm square into 10 power minus 6. Here ke represents kinetic energy of the rotor in unit megajoules. Okay, so j represents moment of inertia of the rotor. Its unit is represented by kilogram meter square. And omega sm represents the synchronous angular speed of the rotor in mechanical radian per second. Suppose if we are specifying in omega s, it represents same synchronous angular speed of the rotor but in electrical radian per second. Okay, so here we are going to assume both mechanical and electrical speed which is related with the number of poles in the synchronous machine. So here generally electrical angular speed will be equal to P by 2 omega sm. So this as equation 3. So I am going to substitute this in first equation. Okay, so I will be getting E suffix ke, that is kinetic energy of the rotor will be equal to half 2 by P whole square omega s. Just cross multiplying to get the omega sm. So 2 omega s by P, okay, whole square into 10 power minus 6 megajoules. Okay, and here after substituting this equation in kinetic energy, we are going to make a constant, means moment of inertia. M represents moment of inertia. So this formula is derived from the previous equation, J 2 by P whole square omega s into 10 power minus 6. So here mainly the moment of inertia is used in this stability analysis. So main also the another constant is used, that is H, inertia constant. So inertia constant is defined as the ratio of stored kinetic energy in megajoules at a synchronous speed to the machine rating in MVA. Okay, it is represented by S. So S represents the power rating of a machine in MVA. So here the kinetic energy is defined by the previous, that is E suffix Ks. Okay, so I'm just substituting the value here. So I'll be getting half j omega sm square divided by S. Okay, so this is to formula to find the inertia constant as well as the moment of inertia which is in electrical radiant. After substituting the inertia constant, I'm going to substitute this in equation 3 and in 5. Okay, so here after substituting the equation for E ke from the third equation in fifth equation, after this I will be obtaining the inertia constant and also the kinetic inertia constant and moment of inertia. Okay, so here we know the omega formula. Generally omega formula is 2 pi f. Okay, so when I am substituting here, 2 will be cancelled and h is by pi f. So this is represented in moment of inertia electrical radiant. Okay, so if suppose I am just converting this to degree mode, radian to degree mode means pi will be converted into 180 degree. Also I am just going to assume this S as a base MVA for finding in terms of per unit value. Okay, so per unit value of M will be represented in M suffix PU SH by 180 F the whole divided by S suffix B base. Okay, so here 180 represents, as I told already, we are just derived in radiant mode. I'm just converting this into degree mode. Okay, so the value of M can be represented in per unit by selecting the base MVA. So if the machine is chosen as a base value, then we will be substituting S equal to SB and this equation will be written as like this. So m per unit will be equal to h by 180f or h by pi f. So both are right. Okay, so in the degree mode and this is in radiant mode. Okay, so this is what the formula to find the dynamics of synchronous rotor of a moment of inertia per unit. Okay, so next topic is swing equation. So swing equation means it's a behavior of synchronous machine during the transient period. So during transient period what happens? Okay, so here the rotor synchronous machine has two torque. One is Te and Tm. So Te represents net electrical or electromechanical torque in Newton meter and Tm represents mechanical torque at the shaft of a rotor which is supplied by the prime mover in Newton meter. Also here Ta represents net accelerating torque, unit is Newton meter. Okay, so here under the steady state condition, when it is in steady state condition, my electrical and mechanical will be equal and the machine will run at a constant speed called synchronous speed. So this will be equal to the accelerating torque. Okay, so we are going to consider one as a generator and another one as motor. So how we can identify which is generator and which is motor? So from the diagram given, okay, so here the motor and the speed are constant. Okay, it is in opposite direction, which is opposite means Te. For generator it is opposite. So from the assumption, so what we have to do is Tm and Te, okay, mechanical and electrical torque, if it is in positive, this will be considered as a generator. Suppose if it is considered as a motor, okay, so my electrical and speed will be in one direction and motor will be in other direction. So means it is an opposite, negative. So Tm mechanical and electrical is in negative, it represents motor. Okay, so from the Newton's second law of motion, the accelerating torque, I'm just assuming this alpha will be equal to d square theta m by dt square. Okay, so this is what the accelerating torque, which will be proportional. So here the torque will be directly proportional to the angular acceleration. Here angular acceleration is alpha. So alpha is d square theta m by dt square. So when I am removing the proportionality constant, J will be the proportionality constant. Okay, so here and J will be the proportionality constant, which is represented as the moment of inertia of the rotor in kilogram meter square. Okay, so from the first equation, so I am just substituting this in equation here. Okay, then Ta is equal to Tm minus Te. This is equal to J d square theta m by dt square. So I can write this Tm minus Te will be equal to the moment of inertia and angular acceleration. And so here the specification. Then the angular displacement means theta m and del m represents, first theta m means angular displacement of the rotor with respect to the stationary reference axis. So here this one is a reference axis and del m here. This del m represents the angular displacement of the rotor with respect to the rotating reference axis. So this one is stationary and this one is rotating. When the angular displacement of the stationary and rotating axis are in synchronous speed, so this theta m will be equal to omega sm suffix into t plus del m. So the angular speed are related to the synchronous speed. Okay. So this equation will be differentiating with respect to t, that is time. Okay. So we will be getting theta m by dt, which is equal to, so this is after differentiating, t will be 1, so omega sm plus d del m by dt. So equation as 4. So again I am just again differentiating with respect to t. So d square theta m by dt square equal to, this will be cancelled and which will be equal to 0. Okay, plus d square del m by dt square. This is as equation 5. So from the equation, so here from the equation 4, we can say that the angular velocity theta d theta m by dt is constant, and which will be equal to omega sm, means this is assumed to be equal to 0. So the condition when it is equal to 0, my rotor angular velocity will be equal to the synchronous speed. Okay, and this d del m, this represents the rotor speed of the synchronism. Okay, so here from the equation 2 and 5, we can write this power, shaft power in mechanical and electrical power in rotor. Okay, so we are assuming the power. So generally we know the power formula 2 pi nt by 60. Okay, so from this I'm going to substitute the mechanical and electrical torque. Okay, so after substituting, the inertia constant will be changed after differentiating all the values, and so here this will be power mechanical actual value will be equal to omega sm tm, or I need only the mechanical because I am going to substitute here, and similarly for electrical. Okay, so electrical will be omega sm te, I need te. Okay, so here I am going to substitute here this. When I am substituting here, so here this will not be there. Okay, j del square del m by dt square will be equal to pm. What is tm and te is pm actual minus pm actual. Okay, so and this is common, so omega sm will be here, I'm just keeping this side. So j omega sm d square del m by dt square is equal to pm actual power in mechanical minus electrical power developed actual value. Okay, so from this we have to find the inertia constant. So as I told already, inertia constant is a ratio of stored kinetic energy to the machine rating. Okay, power machine rating, so which is represented in S. Okay, so this is the formula we derived. So from this, what I'm just going to do is, so I'm just keeping this j omega sm square as it is, and the remaining will be this side. Okay, so after getting this, means kinetic energy half mv square will be equal to, so that is the main concept, so 2hs will be there. Okay, so here 2hs by omega sm which is equal to this. Okay, means into d square del m by dt square, which will be equal to pm minus p actual. So how it is derived means from the equation 2, previous equation, and equation the 6. Okay, the last equation. So both we are going to substitute, and my equation will be 2hs by omega s d square del by dt square, which is equal to pm actual minus p electrical actual value. So how this omega s is changed means, we know the relation, means omega s m will be equal to 2 by p omega s. Okay, so I need this synchronous speed. So I'm just substituting the value, and also this del will be changed. Similarly, for del ACM will be equal to 2 by P del S. Okay, so we are going to substitute in next equation. So here similarly, so we have substituted here. Okay, omega S. So this is my omega S. So this is as it is, equal to Pm minus P electrical. So 2 will be cancelled. The equation is like this. So I need the power per unit value of mechanical and per unit value of electrical. Okay, so here for per unit value of electrical and mechanical will be Pm by S. So even if the machine MVA rating is chosen as base value, then this will be Pm. Value of mechanical power will be Pm actual divided by S, also for electrical. Okay, so from the previous equation we have derived Hs by pi f d square del by dt square minus, so in order to calculate in terms of per unit, instead of P actual, okay, instead of P actual, and this Pm minus Pe will be assumed. Okay, so here this is the equation of for swing. So this equation is called a swing equation, and which is derived from the dynamics of synchronous machine rotor. So it is a second order differential equation, and also it's a non-linear second order differential equation. Okay, so in this video we saw the basics of stability analysis, different classifications of stability analysis, and how to derive the dynamics of synchronous rotor. From this we have derived the swing equation in order to find the per unit value of both mechanical and electrical power. Thank you.